Hi, I'm Steve Sandler, the Managing Director of Picotest, a company that specializes in precision test and measurement equipment. I'm also the founder of AEI Systems, a company that specializes in modeling, analysis, and simulation. In part 1 of this video series, I explained what a power distribution network, or PDN, is, and noted that board-level power converters, such as POLs and VRMs, influence the performance of the PDN through their output impedance. Here in part 2 of this video series, I'll go into more detail on the issue of impedance by explaining the second essential concept of PDN design: keep impedance flat. The first rule in designing a PDN is to keep the impedance of the PDN flat over the frequency range of interest. Discontinuities or peak in the impedance versus frequency curve of a PDN will result in noise signals. A PDN consists of resistance, inductance, and capacitance associated with the voltage regulator, printed circuit board traces and planes, as well as capacitance and parasitics associated with the decoupling capacitors on the printed circuit board. A PDN also includes the package parasitics, such as those of the bond wires and die capacitance of the high-speed logic devices. In order to make the impedance of the PDN flat, the Q of all these resonant circuits must be minimized. This situation leads to another fundamental concept in PDN design, commonly known as target impedance. The target impedance is the maximum tolerable value of impedance on the PDN, which is chosen to limit the voltage noise to an acceptable level. In other words, in order to assure good performance of the PDN, whatever peaks exist in the PDN's impedance versus frequency curves must be kept below the value of the target impedance. The basic idea behind target impedance is that the load and noise currents generated by switching of high-speed logic will produce voltage drops on the supply rails in proportion to the impedance of the PDN. So to limit these voltage drops, PDN impedance must be maintained below a specified value, commonly referred to as target impedance. As a metric for evaluating PDN performance, target impedance has some major limitations. Nevertheless, target impedance remains the most popular technique for evaluating PDN designs. Keep in mind, however, that target impedance is only meaningful across a specified frequency range that is determined by the application. So the basic objective should be to keep impedance as flat as possible up to a system-determined bandwidth. This bandwidth will be a function of the edge speed, the rise and fall times of the load signals, the amplitude of the dynamic current change, and the impedance of the PDN. Maintaining a flat impedance characteristic is the PDN concept that most directly affects developers of board-level power solutions. Designers of POLs and VRMs need to be concerned with the impedance profile their products are creating, since these profiles will affect the impedance profile of the customer's PDN. As with the impedance of the PDN, the goal is to make the output impedance of the power converter flat. Here's an example of a point-of-load regulator whose output impedance profile is not so flat. Notice that the profile changes from the off state shown by the dotted line to the on state shown by the solid line. The impedance curve for this point-of-load regulator is much flatter. And this POL's output impedance is flatter still, but as we'll see shortly, the impedance also needs to be flat at the right magnitude. As I said before, discontinuities or peaks in the impedance versus frequency curve of a PDN will result in noise signals. Now let's look at an example of how this problem can impact one aspect of system performance. Here we see a measurement of PDN impedance as observed at the input to a 10 MHz clock powered by a voltage regulator. Notice the peak in PDN impedance at 8 MHz. Now let's see the effect of this PDN impedance profile on the clock jitter. In this experiment, we'll be modulating the POL output current with a noise signal. But first, we'll measure the clock jitter with no noise modulation on the power supply. In this case, we measure the clock jitter to be 110 picoseconds. Now if we modulate the power supply with a 20 milliamp peak-to-peak sine wave at 1 MHz, we see that our measurement of clock jitter does not change noticeably. However, if we increase the frequency of the signal modulating the power supply to 8 MHz, we see a very sharp rise in the clock jitter up to a value of 800 picoseconds. And then if we continue to increase the frequency of the modulation on the power supply to 25 MHz, the jitter measurement returns to 110 picoseconds. So this experiment demonstrates one impact of a peak in the PDN impedance curve, a degradation in clock performance. In the third and final part of this series, we'll discuss one more PDN concept that designers of board-level power solutions need to know about. That concept can be simply stated as impedance matching is critical. If you have any questions about the information presented in this video, please email me at steve@picotest.com. Thank you.